We are Team 30, Team Dawn Stars. My name is Quentin Schupard. Also part of this group is James Brophy, Joseph Stinziano, Mason Yunt, Han Tran, and Emily Zechkevich. The overall purpose of this project was to design a xylene process unit to be built alongside the existing Gulf Coast plant. The impetus for this being the development of a new zeolite catalyst by our R&D team. The zeolite catalyst produced from toluene equimolar portions of benzene and mixed xylene isomers, as well as some side reactions that necessitated a robust separation process. The plant was expected to operate for an 8,400-hour period in a year, with some shutdown time set aside for regeneration of the catalyst in the reactor. The capacity of this plant was 9,094 pounds per hour of paraxylene, and for benzene it was 26,050 pounds per hour, for a total of 35,144 pounds per hour. Presented on this slide is the block flow diagram for our process. This process can be divided into two overarching categories: the reactor portion and the separation portion. In the reactor portion, the toluene and hydrogen and methane feedstocks, along with the hydrogen and toluene recycles, are fed into the reactor. After this, the reactor product is then fed into our separation process for removing our lights from our heavies. The lights being hydrogen and methane, and the heavies being benzene, toluene, mixed xylenes, and TMB. After the lights are separated from the heavies are then put into our distillation columns. In the first distillation column, our benzene product is separated from our toluene, mixed xylenes, and TMB. Then, in the second column, our toluene is separated from our mixed xylenes and TMB, the toluene then going back to be recycled into the plant and fed back into our reactor. In the third column, our mixed xylenes are separated from TMB, and following that, the mixed xylenes are then fed into our Parex unit, which separates our paraxylene desired product from our meta and orthoxylene undesired products.
So the design process is to create benzene and p-xylene from toluene disproportionation. So our main reaction is going to be toluene coming out with p-xylene and benzene. At the same time, we have three side reactions: toluene hydrodealkylation, xylene disproportionation, and xylene isomerization. So for the first one, toluene hydrodealkylation, it will create benzene and methane from our main reactants, toluene, which can decrease our productivity. Then our product is depleted by xylene disproportionation and isomerization, which will create the undesigned xylene isomers, ortho and meta, and TMB, and at the same time toluene. Even though this toluene can potentially go back into our main reaction and create p-xylene, it's still an unexpected side reaction because it will deplete our main product. The reactor is chosen to operate at 750 Fahrenheit and WHSV of 5 based on p-xylene selectivity and toluene conversion. As you can see on the graph, this is the big red point in which we choose the p-xylene selectivity of around 65% and 31% of toluene conversion, which we think is a good compromise between the two factors to operate our reactor. During the design process, the two most challenging things were separating the mixed xylene and separating the lights from heavies. As you can see on the XY diagram, p-xylene have almost identical physical and chemical properties to M and O xylene, which make using the distillation columns at regular chemical plants very difficult to separate p-xylene from this mixture. That's why we have the specialized Parex unit that Quentin's going to mention in the BFD. Another challenge is separating the lights from the heavies. In our process, in our reactor effluent, we have hydrogen and methane in the mixture with toluene, benzene, mixed xylene, and TMB. in that hydrogen and methane are very volatile gas, which make us have to apply a huge change in pressure and temperature to bring hydrogen and methane into gas phase and separate from the heavier hydrocarbons.
Upon completion of the model in Aspen Plus, a model verification summary was given to us by Dr. McFadden. It was used to determine which hard and soft specifications were met. Most importantly, the two hard specifications were met, meaning that the paraxylene and the benzene products were 99.9 weight percent pure and could be sold for a profit. The two soft specs that weren't met were the xylene and benzene weight fraction in the reactor feed, which was too low, and the product recovery mole percentage, which was also too low. Potential problems for the xylene and benzene not being high enough are that the conversion and selectivity could be affected for the reactions. Potential problems for the product recovery could be a reduction in total revenue. Additionally, Professor McFadden also provided us with a Process Definition Rating Index, or PDRI, which was used to assess the state of the project while it was being completed. PDRI went from a score from 0 to 1,000, with 0 being the best. It was measured after gates 3, 4, and 5. The score after gate 3 was 688. The score after gate 4 was 597. And the final score after gate 5 was 444. The main reason for the decrease from gates 3 to 4 were due to the fact that the equipment was sized, which erased a lot of uncertainty in the process mechanics section of the PDRI. And the main reason for the decrease between gates 4 and 5 were due to the fact that we did an in-depth economic analysis, which we will talk about further along in this, and the fact that process safety was also included in the PFD.
When analyzing the cost of this plant, we wanted to analyze a lot of the operating costs, and one of those operating costs that we needed to analyze was the cost of utilities. From the utilities, we wanted to get a price on them that was given to us. We were given a range of prices that were in the problem statement, and we based those prices, we extrapolated those prices off of the current market price of natural gas, which is at $2.18. From that, we had to use all of these utilities to get the proper energy and temperatures and pressures we needed for each of the systems when operating at those utilities. The utility that was largely used the most was the Dow-therm oil, which was used at 71% of our utility usage. The reason that this value was so high was because the Dow-therm oil was used in the reboilers of distillation 5 and distillation column 7, and they needed to vaporize all of the flow rates that were going through, and the flows going through those distillation columns were very high. Going along with those distillation columns, we found that when we used the condensers, we found that we could generate steam from those condensers in each of those distillation columns. Our idea from generating steam was kind of to subsidize the cost of our utilities because we had such a high utility cost. When trying to generate this steam, we had to supply deionized water to produce the steam from, and this steam could be sold at 60% of the purchased steam that we bought for our utilities. With each of the total utilities, the cost of the utilities for our entire plant for the year was $24,800,000 per year, and the revenue that we generated from producing the steam per year was $4.3 million per year, which, when combining those totals to subsidize the cost of our utilities, gave us a total of utility cost of $20.5 million per year.
Upon analyzing the cost for the utilities, we wanted to analyze our total plant cost. We did this by first analyzing the direct cost for each piece of equipment using Aspen Process Economic Analyzer, or ICRIS. Once this software gave us the direct cost for each piece of equipment, we added in the allocated cost, which included the indirect cost and then the pipe racks and sewers for each piece of equipment. This led us to a total IBL cost of about $101 million, the majority of which comes from the distillation columns, the heat exchangers, and the specialized separation units. As you can see, distillation column 5 alone had 19% of the total IBL cost. The Parex and H2 unit accounted for 30%, and the heat exchangers as a whole also accounted for 30% of the total cost. Once the IBL cost was calculated, we wanted to analyze the OBL cost, which was determined to be $8 million. And in this, it included site development, storage and handling of material costs, and environmental costs. And then with IBL costs, OBL costs now calculated, we were able to add in the miscellaneous costs, and with the three, we were able to calculate the expenses from the escalation and contingency and get our overall total plant cost of $241 million. After analyzing the capital costs for the plant, we wanted to analyze the operating costs for the 15-year period that we would be running in. From 2019 to 2021, as you can see, there was zero operating costs because this is the year, or these are the 3 years that the plant is being constructed in. And then from 2021 to through 2024, the plant is generally increasing to operating capacity of 100%, which is reached in 2024. And then as you can see, from 2024 to 2036, it's about a linear increase in operating costs, which can be attributed to inflation. And in 2036, we had a total operating cost of $247 million, 70% of which was raw material cost alone. After analyzing all the different costs for our plant, we wanted to do a cash flow analysis of it. And as you can see in the diagram, the first 3 years, again, are the years of construction, with 15% of the total capital cost of construction being spent in 2019, 35% being spent in 2020, and the remaining 50% being spent in 2021. And then from 2021 through 2024, again, the plant gradually increased to full capacity, reaching that in 2024, where the first year of catalyst recharge also took place, which must be done every 3 years to ensure that the plant runs properly. Also, between 2022 and 2027, the plant ran at a non-zero depreciation basis, increasing expenses and costs for the plant. By 2037, the plant stands at negative $598 million in cumulative cash flow and a net present worth of negative $223 million.
In order to test the validity of our process, we needed to run 2 different alternative design studies. These design studies included various units in there and different ways to purify your streams or any things along that nature. So the one design process that we came up with, we decided to add a 4th distillation column in our TMB waste stream in order to purify that stream so we could sell it to make a profit off of it. This arises the question is why wouldn't we just optimize distillation column 7 to get a more pure TMB stream instead of adding a 4th one to get the same results. Upon analysis of doing that for distillation column 7, we found that it would cost way too much money to run that distillation column, and the size of that distillation column would be way too safe to run at. So we decided that adding a 4th distillation column to purify TMB would be the best choice. So we came up with this decision because we noticed that when in our TMB waste stream, we had a TMB waste of 93%, and we were losing about 5,000 pounds per hour. So we noticed that over the year, that would be a lot of TMB, and in order to sell TMB, we only needed to reach 99% purity, and we realized that a small distillation column could get us to that purity. So in order to test the validity of this column, we did an in-depth cost analysis of this. The cost analysis from this case, we based off of our initial base case, because we were adding the distillation column so far downstream, it did not affect any of the upstream values. So all of the cost analysis and the utilities and the capital costs of everything else that we had done before for our plant would be the same for this, but all we needed to do was take the cost of the utilities and the capital cost of the column itself. This arises the question, if it didn't affect any of that and it makes our stream more profitable, why wouldn't we just do that as our base case? But due to time constraints and meeting deadlines, we cannot do that. But we decided that further along the project that it could be implemented after construction of the plant itself. Looking at values of this, we noticed that the utilities, the utility of cost of running this distillation column was only $200,000 more than the total utilities, more than the plant itself. This is also due to what I had mentioned before with the steam generation, because we also generated steam from the condenser in that distillation column. The capital costs, after putting it in with our other capital costs, we noticed that it was only $1 million increase in the capital cost. And then running that through the cash flow analysis, we looked at the 15-year revenue of the revenue that this distillation column would generate us, and we get $201 million versus $186 million. This brings us to our net present worth of our plant, and that, which for our base case was negative $22 million, but with this distillation column, it dropped us to negative $187 million per year.
So a sensitivity analysis was ran to evaluate 4 different scenarios, and then they were compared to our base case. So as Mason said earlier, our net present worth was negative $223 million, and our cash flow is negative $598 million. So you can see on our screen, the cash flow is here in green, and the net present worth are your blue bars. So our first case was an increase in natural gas price. So the natural gas price that we used before was $2.18. Now this is historically low. So we averaged the prices over the past 20 years to get a value of $4.29. So with this increase in natural gas price, we saw a cash flow of negative $762 million and a net present worth of negative $270 million. So the next case that we evaluated was a 1-year delay in construction. And with this, we actually saw an improvement in our net present worth with negative $203.8 million, which was very comparable to our base case. And then with our cash flow, we saw a value of negative $600 million. So next we had our raw material reduction, which was where we reduced our raw material prices of hydrogen and toluene by 20%. So with this, we saw a net present worth of negative $127.6 million and a cash flow of negative $266 million. And then finally, the only case that we experienced an actual return on was to increase our product selling prices. Now for this, our p-xylene price was increased by a factor of 1.3, and our benzene selling price was increased by a factor of 1.4. So we still had a net present worth at negative $48.1 million, but our cash flow is actually positive at $12 million, giving us a rate of return of 1.65%. So finally, our team was able to complete all of the tasks in its design of the actual plant. So first, a base case design was established. With this, we had a reactor, a flash separator, a stripper, and 3 distillation columns. The reactor was scaled up from pilot plant data given to us by Nitline Chemicals with our zeolite catalyst. We met all hard specifications with our material being in balance by less than 0.01%, and with both products being in spec, being a purity at a higher value than 99.9%. Next, we figured out the total energy usage of our plant, and that was actually negative 11 million BTU. And then we also calculated our utilities, which came to a cost of 8.65 cents per pound produced from our plant. Next, we used the PDRI throughout our entire process, and finally, as Joe mentioned before, our final score was 444, which was well within the bounds of what we needed. And then we considered 2 alternative cases, and each one was adding the distillation column. And then the one evaluated financially was the one to purify a TMB stream, giving us a third product that was sellable. And then finally, plant economics were evaluated, again, for our base case and for a few sensitivity analyses. For our base case, again, our cash flow was negative $598 million, and our net present worth was negative $223 million. So as a team, we would recommend that this plant not be built in its current state, but we do have several suggestions for going forward. So first, we think that we can improve conversion by probably developing another catalyst. So in its current state, the zeolite catalyst does not have high enough p-xylene selectivity or toluene conversion. So with this, we think that we can definitely improve the selectivity and conversion, giving us an easier separation downstream, so that will also decrease our operating costs. So in our current state, because our separations are so difficult, we do have rather high operating costs. But again, with a better selectivity and conversion, we think that those will dramatically decrease. And then finally, we can consider our alternative design. So adding the third column to purify TMB gives us a third product to sell. And again, having this additional product will just increase the amount of product that we have, which will increase our economics. So again, in its current state, we would not recommend that this plant be built as is, but with several recommendations from our team going forward, we think that this plant has a promising future. So again, we thank you so much for your time, and we appreciate your watching this video. Thank you.
Stop it.